one of the most important features used in the last decade. That is the feature point. The features we have introduced before, like color histogram, age histogram, are all global visual features. That means we extract such visual features from the whole images, like these images, and then we extract the intensity or the color of each pixel, and then construct the color histogram. So this is the so-called global visual feature. And in the following, we will introduce local features, like as we mentioned before, one of the most important disadvantage of color histogram is that it lacks of spatial information. And in the study of the last decade, many studies show that local information is also very important for us to do object detection or many other multimedia content analysis. So many works have been proposed to detect local features. And then in the following, we will introduce one of the most famous local features. What is local features? Local features is also known as interest point or salience point or key point. That means could you point that you can easily point out the correspondence in multiple images using only local information, like these two images. These two images just differ slightly, but you can see this is just a viewpoint change. Okay, a slightly viewpoint translation between these two images. And for this point, okay, the red circle, we can identify the correspondence of the pixels that correspond to the this red circle. So the correspondence between these two images can be linked, can be done by linking this point and this point. Okay, because it is around the corner of the building structure. Okay, and for such case, this point would be a good candidate to be the key points, because we can use such key points to compare or to match these two images. But how about this one? The blue circle. Actually, the blue circle is not a good key point because it is at a smooth area. And this area can be matched to this area. Maybe it can be compared to match to this point, and maybe this point, and maybe this point. And both these 3 points, all these 3 points are at smooth area, and they look very similar to this one. Therefore, the blue circle is not a good candidate to be a key point, because it cannot play an important role for us to match images. So you got the idea of key points. So what kinds of features, what kinds of pixels can be viewed as key points? Okay, the desired property include distinctive and the invariant. The distinctive is that a single feature can be correctly matched with high probability. Just like the example shown above, we can see the corner of the building structure is a good candidate because we can distinctively match the building corner, okay, but not the smooth pixel. Okay, so this is the first desired property. The second desired property is invariance. The extract key points should be invariant to scale, rotation, affine, illumination, and noise for robust match across a substantial range of affine distortion, viewpoint change, and so on. That is, it should be repeatable. So just like the red circle shown above, even if we resize the image, we still can match the building corner. Even if we rotate the images, we also need to match the building kernel. So the feature, how can we represent such a key point? We should design scale invariant, rotation invariant, affine transformation invariant feature descriptor to describe the key points. And given such local feature points, we can develop many applications like object or scene recognition, because depending on the distribution of the local feature points in an image, we may be able to detect specific object, or we may be able to recognize the scene. We can also do structure from motion. We can do stereo match. We can do motion tracking. So many applications can be developed based on robust local feature points. And actually, there are tremendous amounts of studies were conducted based on local feature points in the last decades. And given the desired property, we need to develop several components to extract and describe such key points. The first component is feature detection. We need to locate where they are. We need to locate where the key points are. We then need to develop a description that can describe the key points, such that we can achieve scale invariant and a rotation invariant. We also may need to do a feature match. Okay, that is, we need to decide whether two are the same one, whether two are similar. Okay, such that we can compare different images. We can find specific local feature points in order to detect some specific objects. And in the following, we will introduce one of the most important local feature point, that is called scale invariant feature transform, or SIFT, SIFT in short. And this work was published in year 2004, published in International Journal of Computer Vision. The author is David Law. David Law is very, very famous researchers in computer vision. And the following slides are mainly from Professor Zhuang Yongyu in National Taiwan University. The SIFT features are invariant to image scaling and rotation, and partially invariant to change in illumination and the 3D camera viewpoint. To extract SIFT feature point, we have several main stages of computation. The first step is the scale space extreme detection, and this will be implemented by using a difference of Gaussian, or DOG in abbreviation. So we will use the difference of Gaussian to find the extrema. Okay, and then we will do some refinement to locate the position of the key points. And these two steps correspond to detector. That means it is used to detect the location of key points. The third step is the orientation assignment. So we will try to find one or more orientation and assign name to each key point based on a local image gradient direction. Okay, and after finding the main orientation, we will design a key point descriptor to describe such key point. So the following two steps correspond to descriptor. So the first part is for detection. The second part is for description. And actually, we can repress such description by other method. And we can also repress the detection part by other method. So sometimes when we briefly say, okay, we just extract SIFT feature, that consists of both steps. But sometimes in some literature, you may read that they use some other corner detection algorithm to find the feature, and then use shift descriptor to describe the key point. Therefore, in this case, the keyword descriptor, the so-called shift descriptor, it's just contain the third and the fourth part. Okay, so we can repress the detection part, and we can also repress the description part. So let's go to the first step, detection of scale space, Extrema. The idea is, because we want to make our detected local feature to be scale invariant. Therefore, we try to find some pixel that is unique, no matter in which scale. Okay, so we just for scale invariance, we want to search for stable feature across all possible scales using a continuous function of scale that is called scale space. And in this paper, the author used DOG filter, difference of Gaussian filter, for the scale space because it is efficient and as stable as scale normalized Laplacian of Gaussian. The Laplacian of Gaussian is another method to detect the extrema in scale space, but it should be more computational expensive. And in this paper, they use difference of Gaussian to more efficiently detect the extrema. The scale space of an image is defined as a function and produced from the convolution of a variable scale Gaussian with an input image. So this is the convolution. So given the image, we convolve this image with the Gaussian kernel. Okay, and if you have taken image processing course, you may know that when you convolve an image with a Gaussian kernel, the image will be more blurred. Okay, so this is something like smoothing. Okay, so the LXY sigma is the blur version. Okay, and this is the definition of the Gaussian kernel. Okay, and the so-called difference of Gaussian DOG filter is that we can apply the Gaussian kernel with different parameter, especially the standard deviation parameter. Okay, if we apply Gaussian with higher standard deviation, that means the resultant image will be more blurred. Okay, so this is a more blurred image. Okay, and no, sorry, this is the Gaussian with more that causes more blurred image. This is the Gaussian that causes less blurred image. Okay, the so-called difference of Gaussian means that we minus these two Gaussian. Okay, and using scale space extrema in the difference of Gaussian function convolve with the image, which can be computed from the difference of two nearby scale separated by a constant multiplicative factor k. So the difference of Gaussian, the result of difference of Gaussian is that we can calculate the difference of Gaussian and then convolve the difference of Gaussian with the image. Then we get the dxy sigma. Okay, so the physical meaning of dxy sigma is actually the resultant image, resultant blur image, more blur image, minus by the less blur image. This is called dxy sigma. And this is the illustration showing the scale space. Okay, so by applying the Gaussian kernel with different standard deviation, okay, we can get different degree of blur image. Okay, and mathematically, we can take the difference between two Gaussian to construct the DOG filter. Like we subtract this one by this one and then get this DOG filter. We can then subtract this one by this one and get this DOG filter, and so on. We can also resize the image. Okay, we can also resize the image. So in a smaller image, we can also apply the difference of Gaussian filter to the smaller images. Okay, so the adjacent image scale are subtracted to produce the difference of Gaussian image shown on the right. Okay, so this is the difference of Gaussian images. And this is a real example showing to you that what is the scale space. You can see that this is the original image. And then this one is the image after some degree of blur. And then this is a higher degree of blur, and more blur, and more blur. So you can see that we can, when we apply different Gaussian kernel, we can get blur images in different degree. Okay, so we can do this for the original image. We can also resize the original image like this, and then apply different degrees of blur. Also resize again. So we can get different degrees of blur image at different scale. And then we subtract this image by this image to get the DSY sigma. So this is the difference of Gaussian image here. Okay, and we can subtract this image by this image, and then we get this one, and so on. And for the point that has higher intensity, means we have higher difference between two blur images, and actually such pixels are more important. They are more appropriate to be the key points. Okay. And then the next important step is the local extrema detection. Each sample point is compared to its 8 neighbors in the current images and the 9 neighbors in the scale above and below. For example, for this pixel, we will compare the intensity value. Actually, it's the difference value. We will compare the difference value of this pixel by its 8 neighboring pixels, and also by the 9 neighboring pixels that is in adjacent scale by these 9 pixels and also these 9 pixels. And if this difference value is smaller than all these neighboring pixels, or it is larger than all neighboring pixels, then it is selected as a key point. So it is selected only if it is larger than all of these neighbors or smaller than all of them. So let's go back to previous slides. For some points, for example, this point, maybe this point. For this point, we will compare with the difference of all its 8 neighbor pixels, and then it will compare the 9. If we corresponding to this point, we will compare the 9 pixels at this scale, and also 9 pixels at this scale. And if this value is larger than all its neighboring pixels, we will take it as a key point. Okay, so that is the so-called local extrema, because we compare we compare the difference, the DOG difference. Okay, we compare the DOG difference of this pixel with all its neighboring pixels, no matter it's at the same scale or different scale. Okay, so this is why they call local extrema. So what kinds of scale for us to generate the blur images? And it's impossible because we have infinite solution. We have infinite setting to build the blur image. So it's impossible to sample the whole space. And we need to find a trade-off between the efficiency and the completeness. In this paper, they decide the best sampling frequency by experimenting on 32 real images subject to synthetic transformation like rotation, scaling, a fine stretch, brightness and contrast change, and adding noise. So they collect 32 images and do synthetic transformation. And because these changes were synthetic, so it's possible to precisely predict where each feature in an original image should appear in the transformed image, because they do the synthesis artificially. Just like, for example, if an image, there is a feature point here, and then if we do rotation, this feature point may correspond to around here. So we precisely know the correspondence between any two feature points, so that they experiment different parameters on Gaussian blur, and based on these 32 synthetic images. And here is the result. They conduct the study based on 8 different scales of blur, and the y-axis means the repeatability. Okay, and we can see 2 curves here. The first curve is the matching location and the scale. The second curve is the nearness descriptor in database. Okay, and in this case, what is the solid curve means? That means the percentage of key points that are detected at a matching location and a scale in the transformed images. And this value is for detector, that is for repeatability. When we apply 3 different scales of blur, we are most probably to be able to find the repeat feature point. Okay, so around 90% of feature point can be efficiently detected. Okay, so this is the solid curve mean. The dash curve means the numbers of key points that are correctly matched to a database of 40,000 key points using the nearest neighbor matching. So when we detect such key points, we may describe them as feature vectors. And when we compare feature vectors based on nearest neighbor, by how many percentage can be correctly matched. So this is the value as different scales of blur. And this value is for descriptor. That's for distinctiveness. Okay. And according to this graph, the scale, if we set the numbers of scale is 3, is the best. For larger scale, too many unstable features. Although when we do many scales of blur, we may be able to detect more key points, but this key point may be unstable. Okay, so finally, in this paper, they suggest we just do 3 scales of blur. So let's go back to the example here. We can see in this example we do this is one scale of blur, another scale, and another scale. So here in this example we show 4 scales of blur. Okay, but they, according to their synthesis experiment, they found that using 3 scales of blur perform the best. And this figure shows the numbers of key points that can be detected at a match when the numbers of scale are different. Okay, and as we say before, as the numbers of scale increase, the numbers of detect key point also increase, because when the numbers of scale is 6, we can compare many of them, like 1, 2, 3, 4, 5, 6. Okay, so we can detect the local extrema by comparing this pixel and the neighboring, and the neighboring. And we can also compare this pixel by its neighboring, and the neighboring. We can also compare these pixels by neighboring, and the neighboring. So when we increase the numbers of scale of blurring, we will detect more key points, and we will also match more key points. However, not all of them are stable key points. And we need to find a trade-off between efficiency and completeness. Therefore, in this paper, they use the numbers of scale as 3. Here is another experiment showing the numbers of the parameter of smoothing versus the repeatability. Okay, when we do different degrees of blurring at the same scale, we may increase the standard deviation 1.2 times, 1.4 times, or 1.65 times, and so on. And the solid curve shows the numbers of detected key points. Okay, and the dash curve shows the numbers of match key points. And we can see that as we increase the settings, the numbers of settings of smoothing, we can find more key points and match more key points. However, we need to pay the cost of computation. Okay. So this is the first step. After the first step, we can find the location of key points. Okay. The second step is we try to refine the location of the detected key points. The candidate key points are may be located to subpixel accuracy, and will be eliminated if found to be unstable. So the second step is just a refinement step. Okay, we will reject points with low contrast and poorly localized along an edge. We will also fit a 3D quadratic function for subpixel maxima. Okay, so we may detect the feature point as a subpixel accuracy. For the first step, we may just find this pixel. This pixel is a key point, but the actual extrema may occur around here, and then we use a quadratic function to estimate the location of the key point at subpixel accuracy. So we directly show some sample result here. After the first step, we may be able to find the key points like this. Okay, we will find the local extrema like this. So we may see many local feature points. And after removing the feature point with low contrast or on edges, we can remove a lot of them. So many key points located at the smooth area will be removed. You can see here. So we just remain the feature point that are really extreme. They are really extreme with high contrast. Okay. This is another example showing the effect of filtering. So originally, this is the original image. Originally, we found more than 800 local extrema. So here we can see this kinds of illustration. For the starting point of each arrow, that will be the position of the key point. And for each key point, we will use in this figure, they use an arrow to show the main orientation of this key point. That would be introduced later. And you will see some arrow is quite long and some arrow is short. That is depending on the strength of the gradient. Okay, that will also be explained later. But anyway, originally we found more than 800 extrema, and after contrast filtering, we remain just around 729 filter. And then after curvature filtering, we just remain around 536 key points. And then we can use the quadratic equation to estimate the location of the key point. So after these two steps, after the DOG filtering and the accurate key point localization, we have already determined the location of feature points. Starting from the third step is the feature description. Okay, and to enable rotation invariant, we try to develop a descriptor that can resist to rotation. So how can we do that? By assigning a consistent orientation. The key point descriptor can be orientation invariant. We can estimate the main orientation of each key point. For a key point, L is the Gaussian smooth image with the closest scale. And then we estimate the gradient magnitude at this key point. That is easy to do because we can calculate the difference between the difference between this point vertically and horizontally, and then we can get the gradient magnitude. The orientation can also be calculated based on the arctangent, the vertical difference divided by horizontal difference. Okay, for any key point, we can find the gradient magnitude and the orientation. Okay, and basically we can quantize the orientation into 36 bins. Okay, and this is an example showing the gradient magnitude and the orientation. This figure shows the horizontal gradient difference. Horizontal gradient. This is the vertical gradient, and this is the overall magnitude. And the pixel with larger intensity value means higher gradient. Okay, and this figure shows the orientation, gradient orientation. It is shown in color, so different color represent different orientation, different direction. So by focusing on this key point, for example, this key point, we can calculate the gradient magnitude and the gradient orientation for each pixel. Okay, so right now the key point is located at this point, and we can find a patch centered by this pixel, and then calculate the gradient magnitude and the gradient orientation from each pixel in this patch. So how can we do that? We actually, before calculating the gradient magnitude and the orientation, we first do a Gaussian blur. Okay, we do a Gaussian blur centered by next pixel. So first we do a Gaussian blur, and then we calculate the gradient magnitude and the gradient orientation for each pixel. So here we can see that these few pixels have higher gradient, and these few pixels have higher gradient. And the direction for these few pixels, the direction of the gradient is direct to the above. And for next pixels, they have different gradient orientation. And based on such information, we can develop the descriptor. But before that, actually, the gradient magnitude will be convolved with a 2D Gaussian kernel to do some smoothing, because we try to emphasize the central part of each patch. So we finally construct the weighted gradient magnitude. So each sample add to the gradient histogram is weighted by its gradient magnitude and by a Gaussian weighted circular window with a sigma that is 1.5 times that of the scale of the key point. If you are interested in the very detailed technical detail, please refer to the original paper. But anyway, we calculate the gradient magnitude, and then we weight the gradient magnitude by a Gaussian kernel, and finally we can get such result. And based on the weighted gradient magnitude and the gradient orientation, we can construct a gradient histogram, a weighted gradient histogram. In this histogram, the x-axis means the gradient orientation. And right now, we quantize the orientation into 36 ranges. And the y-axis means the strength of the gradient corresponding to some specific orientation. Okay, so we just accumulate the weighted gradient magnitude. For example, this direction may be like this direction may be like this, and then these two gradient orientation correspond to the same direction. So we may accumulate the weighted strengths together to form the value of this bin. Okay, and finally, by checking all the pixels in this patch, we can construct a weighted orientation histogram. Okay, so here the bucket 1, the histogram bin number 1 corresponding to the angle from 0 to 10, and the bucket number 2 may correspond to the angle from 10 to 20, and so on. And based on such weighted orientation histogram, we will find the peak. Okay, and this peak will represent the main orientation of this key point. Therefore, in this example, the key point here, the main orientation of this key point would be the bin corresponding to 20 to 30 degrees. Then when we illustrate this patch, we will draw an angle at this direction. And this is the direction of the main orientation. Okay, and sometimes we may construct a gradient histogram like this. Okay, if the second peak, the value of the second peak is larger than the 80% of the first peak, then we will say that this key point have two main orientation. So in this case, generate duplicate key point. We will generate duplicate key point at the same location. One with the orientation at 25 degree and one at 155 degree. Okay. You in real design, you may want to limit the numbers of possible multiple peak to 2. Okay, so in many applications, we may see some key points. There are 2 arrows starting from this key point. Okay, this is because we allow 2 main orientation for each key point. So go back to the example. We will see that for the remaining key points, we now estimate the weighted gradient magnitude and the gradient orientation. And then we show the main orientation. Like for this key point, the main orientation is this. The main orientation of this key point is this. And the length of the arrow indicate the strength of such gradient. So if the gradient histogram is something like this, the strength will be very large. And sometimes the gradient histogram may be just like this. The strength is smaller. And we use the length of the arrow to show the strength. After determining the main orientation of each key point, we now can finally design the local image descriptor. The image gradient magnitude and the orientation are sampled around the key point location, and the coordinate of the descriptor and the gradient orientation are rotate relative to the key point orientation. So let's see this example. Given the key point location here, we check the patch centered by this key point, and then in this example, we may divide the patch into 4 smaller patches. And for each smaller patch, we will construct an orientation histogram. Okay, and assume that the orientations are quantized into 8 directions. And then in this, for example, for this small patch, we can construct an 8-dimensional orientation histogram. And for each histogram bin, the value is generated by accumulating the gradient magnitude. Okay, and the most important part is because we have already determined the main orientation. Therefore, for constructing the orientation histogram, we calculate the difference, or we calculate the increased angle between the pixels gradient orientation to the main orientation. For example, right now the main orientation is here, and then for this pixel orientation is here. Then when we construct the orientation histogram, we don't use such orientation. We actually use the increased angle theta to construct the orientation histogram. Okay, and this is why we can achieve rotation invariant when we describe the key frame, the key points by such image descriptor, because all the value in the orientation histogram is relative to the main orientation. So even if we rotate the whole images, the main orientation also change to that direction. And then because we use the relative orientation, we still can get the same image descriptor. An experiment in this paper used 4x4 descriptor compute from 16 by 16 sample area. That means centered by a key point, we construct a 16 by 16 page, and this page is divided into 4x4, totally 16 pages. And for each small patch, we can construct a 8-dimensional orientation histogram. So the descriptor is formed from a vector containing the value of all the orientation histogram entries corresponding to the length of the arrows. So finally, we have A orientation. For each small patch, we have A orientation. And right now, we have 16 orientation histogram. Therefore, the total dimension of the shift descriptor is 128. Okay, and to reduce the effect of illumination change, the vector is normalized to unit length. And also to reduce the influence of nonlinear illumination change caused by camera saturation or illumination change with different orientation by different amounts, we threshold the value in the unit feature vector. And to each be no longer than 0.2, we just truncate such feature value into 0, and then we normalize it again. And this process is to suppress the noise or to emphasize the larger feature value. So why 4 by 4 by 8? Why we divided the patch into 16 smaller patch? Okay, this setting is also derived based on experiment. So right here, we check how we divided a big patch into smaller patch. That would be 1 by 1, 2 by 2, 3 by 3, 4 by 4, or 5 by 5. Okay, and for each small patch, we may be able to construct 4-dimensional orientation histogram, 8-dimensional or 16-dimensional orientation histogram, and this is the performance evolution. The y-axis is the correct nearness descriptor. Okay, and then we can see when we divided the big patch into 4 by 4 smaller patches, and when we use the A orientation histogram, we can achieve the best performance. So this is why finally this paper they use 4 by 4 by 8. Okay, that means we have 16 smaller patches centered at the key point, and for each small patch we construct a 8-dimensional orientation histogram. So after all these steps, we have already detected the position of key points. We do key point location refinement, and then we calculate the main orientation of each key point based on the patch centered by this key point. And finally, we construct a 1 and a 28-dimensional shift descriptor. Therefore, we can transform each key point into a 1 and a 28-dimensional feature vectors. And then, depending on the application you try to develop, we may need to do feature matching. Okay, for a feature X, we want to find the closest feature X1 and the second closest feature X2. If the distance between X and S1 and the distance between X and S2, if the ratio of the first distance to the second distance is smaller than 0.8, then we say that the feature X is matched to X1. Okay, that means to the first match and the second match, if the first match is much better than the second match, then we will say that the feature X is matched with feature X1. And this is the simple way in this paper to do feature matching. And based on shifted descriptor and the feature matching scheme, we can develop many applications like recognition. Here we have a sample image, okay, and we can extract many shift point from that. For example, from this shift point, now we use a square to show the key point, and we can see that the different square may have different orientation. That is indicative of the main orientation, and we can also see these squares are in different size. That is to indicate the strength of the main orientation. Okay, so that's quite similar to the arrow representation. Okay, and in the literature, we may have several ways to show the main orientation and the gradient magnitude. Okay, so in this example, we can extract many shift features. We can also extract many shift features from that, and then we may find that this feature match with this feature, this feature match with this feature, this feature match with this feature. And if we can find many feature match between two images, we may say that in this image there is an object. There is an object similar or the same as this object. So this is why we can do object recognition. We can use shift descriptor to do image retrieval. Like given a query image like this, we just compare this image with images in the database. And the way we do this is we extract shift descriptor from the query images, and we also extract shift features from all the images in the database, and then we just do feature matching. And if the numbers of match key points is larger than a threshold, then we say that this figure is matched with this figure. And this is why we can do image retrieval. So here is another way to show the shift descriptor. We use an ellipse, okay, and the orientation of the ellipse indicate the main orientation, and you can see the size of the ellipse indicate the strength. Okay, and we can find some match. For example, this point match with this point, and this point match with this point. And if the numbers of match feature point is larger than the threshold, then we say that these two images show the same scene or the same object. Here is another example. We can give this query and find similar images. We can also do stereo matching. Okay, assume we have a stereo camera. Then we have an image captured by the left camera and another image captured by the right camera. Or maybe we have only one camera, but this camera slowly move. Then we can find the correspondence between temporarily adjacent images. So this point may match to this point later. So this point may match to this point, and this point may match to this point. And then we can do localization, we can do motion estimation, we can do camera calibration, and so on. Shift descriptor can also be used in augmented reality. Okay, so if we try to put a virtual object on this can, okay, so first we need to construct the model. We can construct the model, and then we can put the virtual object on the can. And when we move the camera, this object will change correspondingly. Therefore, it just look like this object is always located at the top of the can. And this can be done only if we can accurately determine the match between different images. It can also be used in automatic image stitching. By given these two images, we can find the correspondence between them. So first, we find the shift descriptor from these images and these images. We then find the correspondence between them, and then we stitch them together and do some blending. So finally, we can construct a panorama. And this work can be extended to multiple images. So we can extract shift descriptor from each image and then compare any two images to find the correspondence between them. And then finally, we can find that, okay, these images are similar, these images are similar, these images are similar, and so on. And then finally, we can construct such panorama images. And this is a very impressive work to do automatic image stitching. We also use this to do near duplicate detection or copy detection. So we can compare the videos, maybe the news video broadcast by different TV channels, and then we can know that the news story number 1 is similar to the news story number 27 broadcast by another TV channel. Okay, so we can do the near duplicate detection. We can also use shift match to find the most important images. Just like this, an image is more important when it is if it is similar to many other images. Okay, so we can use the numbers of match feature point as a similarity between different images. And then we can measure how likely this image is similar to others. And the image that is most similar to all others is viewed as the most important one. So that we can do photo summarization. We can find the most important photo. And also there is a very impressive application that is called PhototoReason. Okay, you can just Google this term to find a demo video that is very impressive. So for example, given a lot of images captured around the area of the Notre Dame in Paris, they can automatically estimate the correspondence between different images and then construct a 3D model of the Notre Dame. And then they develop a 3D photo browsing interface such that we can browse, we can see the Notre Dame from different angle, and we can change from this photo captured by some user to another photo captured by another user. So this is a very impressive demo. You should take a look. So please Google PhototoReason, and then you can find the demo. And if you are interested in extracting shift feature, you can directly go to David Low's homepage, and then you can download the executable program or the source code. Okay, you can also see some resource on Wikipedia.